Welcome, everyone. Today, we are exploring a major shift in AI, moving away from standard RAG toward a new post-RAG architecture called retrieval as reasoning. Traditional RAG relies on brittle chunk retrieval, treating information as static, isolated text chunks that often lead to unnavigable pathways. In contrast, our new approach builds a traversable, interconnected knowledge base where information is dynamic, evolving, and enables true relational reasoning. Why is this shift necessary? Because the current reasoning bottleneck is actually structural, not algorithmic. Standard systems face a matching versus reasoning problem, meaning they excel at finding local facts but shatter when agents must follow cross-document relations. They also act as a single-shot black box, fetching fixed context upfront without the ability to dynamically revise their search based on partial evidence. Furthermore, without a self-correction loop, these structured bases suffer from silent degradation over time, accumulating dangling links and unsupported facts. This represents a massive knowledge paradigm shift. Standard RAG relies on flat text chunks that cannot traverse intermediate nodes, while Graph RAG uses machine-readable fragments that suffer from lossy summaries and high costs. LLM Wiki, however, provides structured, human-auditable interlinked wiki pages. The core bottleneck here is simply a one-time index compilation cost, which unlocks massive long-term value. Allow me to introduce LLM Wiki, the very first agent-native retrieval system. It operationalizes external knowledge into a compilable, composable, and self-evolving structure using three core pillars. Pillar 1 is compilability, which transforms raw text into structured wiki pages with explicit bidirectional links. Pillar 2 is composability, a traversal engine that exposes search, read, and link following operations to AI agents. Finally, Pillar 3 is evolvability, an immune system powered by a persistent error book that drives continuous self-correction. Let's break down Pillar 1, compilability, which builds the traversable substrate. Instead of simply chunking documents, we compile them into a persistent, interconnected wiki. This architecture includes a global index for a comprehensive catalog, directory indices organized into semantic sections for browse-first traversal, and source archives that maintain original articles for auditable provenance. If we look at the anatomy of an agent-native knowledge node, we see a highly structured format. It includes metadata and aliases so agents can locate pages under varying names, alongside key facts that reorganize dense source text into highly scannable, atomic claims. Crucially, it features bidirectional Wika links providing explicit traversal paths, which is the critical affordance for multi-hop reasoning. It also maintains source references to preserve strict grounding to the original text. Moving to Pillar 2, composability introduces a dynamic traversal engine. Retrieval becomes an active reasoning loop using agent tools like wiki_search and wiki_read. For specific questions, the agent uses search-first traversal, reading, and following explicit links to bridge knowledge gaps until a sufficiency check is passed. For exploratory queries, it uses browse-first traversal, reading directory overviews and selectively drilling down to mimic human research. To truly test this, we use the 4-hop multi-document test from the 2Wiki multi-hop QA benchmark. The query asks, which film has the director who is older, the Gamecock or Monster a Go-Go? To answer this correctly, an AI agent must identify the films, discover their directors, locate the directors' birth dates, and then compare them. When we try this with standard retrieval as lookup, the system fails. Dense RAG easily retrieves passages matching the films, but it hits a semantic distance barrier. The director biography pages containing the crucial birth dates are semantically distant and completely missed by the system. As a result, the agent is forced to hallucinate an answer based solely on film descriptions. However, with retrieval as reasoning, we achieve a triumph. First, the agent searches for both film titles and batch reads their wiki pages. Second, It spots explicit director links inside those pages and uses them as discoverable waypoints to directly reach the biography nodes. Finally, it extracts the exact birth dates, compares them, and correctly deduces that Herschel Gordon Lewis is older than Pasquale Festa Campanile. But managing this interconnected knowledge brings us to Pillar 3, the threat of knowledge entropy. LLM-compiled knowledge structures inevitably introduce errors that compound over time. Structural validity errors, like dangling links, account for 29 to 63% of detected issues, alongside incomplete pages and malformed references. Without a persistent self-correction loop, the system's traversability degrades silently. This is why we built evolvability through the error book immune system. It is a persistent constraint accumulation loop that prevents silent degradation. Validators discover errors, trace them to root causes, and generate natural language constraints. These constraints are then injected into future compilation prompts, while a two-layer repair system executes automated code and LLM fixes to heal affected pages. The empirical proof shows that LLM Wiki scales brilliantly with reasoning depth. On the 2-wiki multi-hop QA benchmark, standard retrieval drops off as query complexity increases. In contrast, LLM Wiki's advantage widens significantly on complex 4-hop queries, reaching an incredible 0.983 F1 score and beating the strongest graph baseline, LiteRAG. Ablation studies confirm that removing progressive traversal drops performance dramatically, proving that the structure is most powerful when actively traversed. LLM Wiki also masters multi-document synthesis. While standard methods perform fine when answers live in a single source, LLM Wiki truly excels when evidence is dispersed across multiple documents. On the authtrace benchmark, it outperformed HippoRAG2 by an impressive 8.9 accuracy points on high multi-document questions. Reorganizing raw source text into concise facts is what uniquely enables this rapid cross-document synthesis. Ultimately, this creates the agent-native knowledge flywheel. Structured compilation creates the traversable substrate, compositional traversal exploits that structure for iterative reasoning, and the error book constantly refines the compilation. LLM Wiki is not merely a retrieval tool, it is a living knowledge organism. The era of flat retrieval is over, because knowledge must be built to be reasoned with. Thank you.